Hello, Geography 212 class. This week we're going to be taking a look at Chapter 10, Mid-Latitude Weather Systems. What this chapter looks at, it looks at high-pressure systems or anticyclones, low-pressure systems, mid-latitude cyclones, and takes a look at fronts as well. Toward the end of the chapter, we're going to take a look at certain types of local winds, what we call that. So let's get started here. Mid-latitude weather systems. First slide we're going to take a look at is source regions for air masses. Now remember, these air masses, we label them things like maritime polar, continental polar, so on and so forth. We did this earlier on in the course. I think it might have been back in chapter 1, but let's just take a look at this to refresh your memory here. If we start up in the North Pacific, you can see that maritime polar, or MP air, is going to originate over the North Pacific. And recall that air masses are going to take on the characteristics over the land at which they are sitting. So a maritime polar air mass is going to be rather moist and cold. Okay, if we move over to the Arctic, over northern Canada, we can see that continental polar air masses will develop over that dry, cold land. So CP air then is going to come out of the Canadian Arctic and subarctic. You can see as we move across to the North Atlantic that MP, or maritime polar air, can also develop over the North Atlantic. Although that air does not impact the United States that often, it will occasionally advect into the northeastern part of the U.S. Now, if we go down to those red air masses, this is just going to mean they're warm. If we go off the South Pacific there, we've got the maritime tropical air, MT air, that can advect into our area here in the Southwest. And this maritime tropical air can develop over the Gulf of Mexico and also over the southern Atlantic Ocean. And then over the interior, you can see we get continental tropical, or CT air. This is going to develop over the southwest during the summertime when ground heating is at its maximum, and then that heats the air. CT air does not develop after summertime, so it's only a summertime phenomenon. Now, you know that fronts form at the boundaries. We've talked about this before. All right, so in other words, air masses that form up over different areas are going to be of different density because their temperature and moisture content is different. So we already know about these fronts, so let's just move on and get into some specifics here. We have a warm front and a cold front. Up at the top, what you see is a warm front. This is simply warm air advecting or moving into cold air. Now, warm fronts move slower than cold fronts because warm fronts have a more difficult time moving the cold air along the surface. You can see from the depiction at the top that the warm air overruns, this is what we call overrunning, overruns the cold air and slowly erodes that air down from the top. And notice how shallow an angle that is on the warm front, all right, down at the surface, or near the surface. And as you can see, you do get a progression of clouds as the warm air is lifted and condenses up over the cold air. Furthest from the warm front, you start with cirroforms. That's the CI and C, cirrostratus. And then as the front approaches and gets closer, these clouds are going to lower. We're going to get into middle clouds. Altostratus is what's depicted there. And then once the rain starts falling, we've got the nimbostratus. And then finally, near the front, we could get down to stratus clouds. Okay, down below, cold front. This is the cold, dense air that basically bulldozes up under warm air. A cold front's going to move more quickly at the surface than a warm front. It has an easier time displacing the warm air. Now, unlike a warm front, we get a pretty steep front along the cold front. And you can see we get rather rapid uplift in front of the cold front. And in this case, we're looking at a cumulonimbus cloud develop. That doesn't always happen, but it is a fairly typical event. Right, you can take a look at this slide, read through it, but it's basically just what I was talking about, so I'm going to move on. But that's just there for your reading to see if that'll help you understand it. And the same thing with the cold front here, okay? Now, an occluded front, this is an interesting one. what happens is, remember I mentioned that a cold front can move faster than a warm front. So once a low pressure system develops and starts moving across the United States, as it matures or gets older, the cold front can actually catch up with the warm front. And when it does that, we get an occlusion. Now you can see there's three types of these occlusions down here because it depends what kind of an air mass is moving into the warm front and what type of an air mass that warm front have been moving into. So you're actually looking at the intersection of three different types of air masses when we have an occluded front. So let's just work through them here. A cold occlusion, that first bullet there, it's when the air behind the cold front is colder than that cooler air ahead of the warm front. And I'll show you a depiction of this in a second. Actually, let's take a look at it right now. The cold type. Look at the left here. So we're getting a cold front's moving in, it catches up with the warm front, and now that warm front is above the ground, but the colder air moving in is colder than the cold air that was in behind the warm front, so it's also displacing that cooler air that's depicted as cold on the right side of the screen. So that's a cold type of occlusion. That's going to happen when we get continental polar air moving out of Canada, moving into the eastern United States or eastern Canada. That's typical in the wintertime. So we go back here, we can get a warm occlusion. And that's when the air behind the cold front's not as cold as the air ahead of the warm front. Let's take a look at that one. That's going to be the one on the right here. So if you take a look at that, you can see the air moving in, air on the left, it says cold. It's not as cold as the air to the right. Therefore, it's going to move up. That colder air actually get displaced by the colder air to the right. That is called a warm type occlusion. And that can occur in northern portions of the west coasts, Europe, or the Pacific Northwest. That's where we typically get them. All right. And then finally, we can get a neutral occlusion where there's a little difference between the temperature and or moisture content of those air masses. And generally, all you're going to get there is you're going to get a wind shift. You could get a band of cloudiness and some precipitation. All right, so there you go. The three different types of occluded fronts: the cold occlusion, the warm occlusion, and a neutral occlusion. In terms of this name, extratropical cyclone, all that means is extra means outside. So we're looking at cyclones outside of the tropical regions, be here in the mid-latitudes, and they also are referred to as mid-latitude cyclones, but I like to just call them low-pressure systems. That's the general term we use here, okay? What this table 10.2 is looking at are just the general characteristics of a mature extratropical cyclone or low-pressure system. There's not a lot that I'm going to read through there. You can take a look at it. Some of the more important issues there, though, would be how large are they? So the diameter there can be 1 to 2,000 miles in diameter, typically quite a bit larger than a tropical cyclone. The maximum winds, it suggests they're 35 to 45 miles an hour. However, some of these very strong extratropical cyclones that originate down in the Gulf of Mexico tend to develop winds twice that speed, and we've seen that in the past occasionally. They can occur at all seasons, but most of the time they're going to occur in the wintertime, or we certainly get more of them in the winter. That's what that DJFM means: December, January, February, and March. Okay. I'm going to leave that right there, and you can take a look at that list on your own. Okay, this is what we think. Well, this is how we observe cyclones or extratropical cyclones developing in the mid-latitude regions. You can see they're going to go through 4 stages here. Let's look up at the top at A. It's referred to as an incipient cyclone or cyclogenesis. How do we get a cyclone, extratropical cyclone, to develop? Well, first of all, we have to have a front. You can see that we have a front there in A. We have a cold front and a warm front, and we're just... Typically, the way these things really start is there'll be a stationary front. A slight bit of low pressure will form along the front, and then we get cold air moving into warm air and warm air moving into the cold air, because look at the L there in A. What is the circulation pattern? Counterclockwise around the low. So if you can envision the counterclockwise wind around that low, you're going to see it's going to be pushing the cold air into the warm air on the western side of the low pressure system to the left, and it's going to be moving that warmer air up into the north on the eastern side or the right-hand side. So the low pressure is just getting developed there with its fronts. Now look down to B. Look how far the cold front has traveled now compared to the warm front. And now this is referred to as a wave cyclone. Again, these are very typical. These typically form in the wintertime in the United States. If you look down to C, now we can see the cold front has started to catch up with part of the warm front, and we have the beginning of an occlusion in C. You can see that the way occluded fronts are depicted on surface analysis maps are we alternate the sharp point with the rounded symbol of a warm front, all on the same side, unlike a stationary front that alternates them on either side of it. Also, if you happen to get a color-coded map, you're going to see that occluded fronts will always be shown as purple. Then we look finally down at D. This is what we call a mature low pressure system or extratropical cyclone. Look at the length of that occluded front. Okay, that shows that that's several days old or more, this low pressure system, and a great deal of that cold front is caught up with the warm front. Then if you look over at the satellite image in the lower right, you can see that that's showing what that surface analysis is showing in D. There's your satellite image of what a mature extratropical cyclone is going to look like in the U.S. Look at the length of that occluded front. Okay. There's a term that meteorologists will sometimes use as a bomb or a cyclone bomb, and you will see this occasionally used in meteorology, but it does have a definition to it. It's defined as a central pressure drop of at least 24 millibars in 24 hours. So think about what that means. It means that this low pressure system is developing incredibly rapidly, all right, very rapidly. And these things can develop very strong winds, very intense precipitation. So cyclone bombs, and typically where you're going to see this is wherever a low pressure system in the United States can feed into or tap into warm ocean water, either along the Gulf of Mexico or along the east coast of the United States. Sometimes these types of extratropical cyclones will be moving up the east coast of the United States and develop rapidly into these cyclone bombs. All right, now we have a very important concept here for extratropical cyclones, and that's what we call the 4 quadrants. All right, so in other words, if you look at these, let's look at A, for example, over this surface analysis depiction here. If you could draw quadrants, in other words, 4 quadrants, a northeast, northwest, southwest, and southeast, you're going to find different weather there. So let's work down through these 4 sectors or quadrants. So we'll start with the northwest. If you go into the northwest section of where that L is, the low pressure, what are you going to find? You're going to find northwesterly flow of wind, northerly and northwesterly flow of wind, and that's going to be cold air advection. Look where it's pulling that air out of. It's pulling that air out of Canada in this case. It's going to be cold and dry. So the northwest sector of a low pressure system is always going to be the coldest sector. Okay, so keep that in mind. It's also going to be relatively dry. Now, let's take a look and move down into the southwesterly quadrant. You can see that the wind there could come from the northwest, but also it could come from the west. All right. In this particular sector, in the southwest sector, it's not going to be as cold as the northwest sector. I mean, it's further south for one thing. The advected air is coming more from a westerly location, not so much a northerly location. And the characteristics there and behind the cold front are it's going to be relatively dry. All right. So both the northwest and the southwesterly quadrants tend to, and I really want to underline that word, tend to be dry, relatively dry. All right, let's go to the southeast quadrant. Okay, that's going to be the air out in front of the cold front. Look at the wind direction there. It's pretty much coming out of the south, could sometimes be coming out of the southeast. That's going to be warm air advection. So the southeastern quadrant is going to be the warmest sector of the 4 sectors around a low pressure system. The other issue is you can see as a cold front moves into the southeast sector, it's going to be causing sharp uplift. And if you look at depiction C down below, you're going to see this relatively narrow band of typically cumulonimbus clouds, thunderstorms, that sort of thing. But further out in front of that cold front, you're really going to be relatively dry in the southeastern quadrant. Now, the northeast quadrant tends to be where all the action is, because if you take a look at where the warm front is, think of that warm air now, hits that surface warm front, it has to override and overrun the cold air. Think of all that lift we're going to be getting in the northeast quadrant. So the northeast quadrant tends to have the most extensive cloud cover and the heaviest precipitation. All right, so it's important to understand what goes on in all these quadrants, because once we determine what track one of these low pressure systems is taking, then we can figure out what kind of weather we're going to get in certain locations in the United States. All right, so let's just summarize that, review that for once more. Starting with the northwest quadrant, it's going to be the coldest quadrant. It will have some precipitation, but generally it's pretty light and spotty. Okay, we get down into the southwestern quadrant. It's a relatively dry quadrant. It's going to be warmer than the northwest quadrant, but still probably the second coldest quadrant. The mildest air is going to be down in the southeast quadrant. This is going to be southerly airflow. No precipitation except along the front edge of that cold front as it causes a sharp lift out in front of it. And then finally, the northeast quadrant, we have this extensive amount of overrunning of warm air over cold air. We're going to have the most extensive area of clouds and precipitation. So the four quadrants are sectors then of low pressure systems, a very important concept in meteorology. All right, let's take a look at these principal cyclone tracks, and really I'm just going to boil this down to four that you should be aware of, because I'm going to tell you the four most important ones in the United States, really. Okay, starting in the north, Alberta. Yes, we get these, we call them Alberta clippers, that tend to develop in the lee of the Canadian Rocky Mountains near the city of Calgary, Alberta. And then these, you can see the typical track that they're going to take. Now, these low pressure systems are extratropical cyclones. Because they develop over the eastern part of the Rockies that far north, they're not that moist, okay? They're relatively dry. These sort of systems will just give us light precipitation, generally light snow across the northern part of the U.S. in the wintertime. Now, the next one down the North Pacific, also just called Pacific lows, these are going to form out in the Gulf of Alaska and the North Pacific Ocean. These are going to be much moister than the Alberta lows, and so these can be major storms that come across. They come off the coast of the Pacific Ocean and move across the United States. These can be major storms. Okay, the third one down that you should be aware of is called the Colorado lows. These typically form up in the lee of the Rocky Mountains, you know, near Denver, Colorado Springs area, that sort of thing, and then move generally off to the northeast in the United States. These can be significant storms if they dip far enough south to tap into some of that Gulf of Mexico moisture. Okay, they don't always do that, but they can be pretty big storms. Generally, we call them moderate precip. And then the fourth one is referred to as the East Gulf. I generally refer to them just as Gulf lows, but look where they get started and look how they track. Almost their entire length, they're tracking over very warm ocean water. That means these are the ones that can develop into the most active extratropical cyclones in the U.S. These are the ones that can develop into cyclone bombs, and in the past we've seen winds on these things reach hurricane force, which is 74 miles an hour. So there's your principal cyclone tracks. Just to summarize the ones you really should be aware of: Alberta, Colorado, North Pacific, and the Gulf lows. Okay, now going back to the sector, the four sectors we're talking about, here's a hypothetical situation that a weather forecaster in the United States is going to confront. We've got a low pressure there, that red L, sitting over northeastern Colorado. And we're taking a look at if it follows hypothetical track A or hypothetical track B, what is the weather difference going to be to Chicago? So let's take a look at it. In other words, if that low tracks across the A track, okay, what's going to happen is the center of that low will be continuously either to the west or north of Chicago. What that's going to mean is Chicago's going to tend to stay in a southerly airflow until the cold front passes, which means really that if it follows track A, Chicago is going to get very little snow. It's probably going to get mostly rain as it stays in the warm sector out in front of the low. It's going to be in that southeastern sector for a lot of the time. So if the forecaster's thinking it's going to follow track A, that forecaster is going to predict very little snow, just rain. All right, let's say it follows track B. All right, if it follows track B, note how the center of that low will stay to the south of Chicago. And remember, lows pull in air toward them. This is going to keep Chicago up in the northeastern and northern part of this low pressure system in a northerly airflow. It'll end up getting into that northeastern quadrant and probably getting a significant snowfall. So what a difference, you know. If it follows track A, Chicago will just get some rain, you know, no big deal. But if the low follows track B, Chicago could be in for a significant snowfall. This is where it becomes very important that weather forecasters get this right for an extratropical cyclone's path, okay? Anyway, you can read through that table and the book. I would take a look at that too. I'll give you some more detail. And again, this is just depicting, once again, the different types of weather in those four sectors. So let's take a look at it. You can see the low pressure system sitting there in Illinois. Look off to the northwest, some snow flurries. It's going to be remember, it's the coldest sector, so that any precipitation in the winter is generally going to be some light snow up in there. If we look down in the southwestern quadrant, it's drier yet. Those little triangles are just depicting showers. So some snow showers, rain showers perhaps right along the front, and cool. If we look into the southeastern quadrant, we can see a line of thunderstorms out in front of the cold front as it approaches, but otherwise it's a very warm sector in behind the warm front. And then up in the northeast quadrant, we can see a lot of rain falling in there, as we would typically see. And then further north, up in Michigan and Ontario, we can see that they're far enough away that it's snowing. Okay, so again, just depicting the four quadrants of the four sectors once again. Let's take a look at this. I'm gonna skip this because this is going to have something to do with our monsoon that I'll talk about at another point. Okay, also in this chapter, they talk about these local and regional circulation systems. This first one's depicting what we call land or land and sea breezes also occur along the lake. Let's look at the top picture there. This is going to be during the day. The sun is out, and you're along a coastline of either a large lake or a seashore under ideal conditions. Sun comes up, the land is going to heat up more than the water is, okay? So what happens is we start developing, land heats up, it heats the air above it, and that air rises. So if we lift air above the land, we're going to be creating some lower pressure at the surface, and so the air off the ocean is going to flow in to meet that low. And then it sets up this cell motion, as you can see here. In other words, during the day then, under ideal conditions, the wind will be blowing off of the lake or off of the ocean onto the land. That's your land breeze. But then let's take the same place. The sun sets. The ground cools off very quickly, but the ocean or large lake water will retain this heat. Therefore, the opposite happens. Since the water is warmer now, it warms the air above it and causes the air to rise, creating a little bit of low pressure over the water. So the air over the land flows out to meet that, and we just get this opposite circulation, okay? And that's going to be a land breeze. So the top is your sea breeze during the day as the wind's flowing off of the ocean to meet that lower pressure on the land. And then at night, we're going to get this land breeze as the air from the land blows out to the sea. Now, another thing we can get set up, again, under calm, clear conditions is what we need to see. We need to see that happen to get this. Certainly here in northern Arizona, we get a lot of this, okay? The top, we're going to call this a valley breeze, okay? This is where the sun is beating down on the surface and the lower slopes are getting warmer than the upper slopes. So that lower slopes that are warm are going to heat the air above it, and as you see the arrows, it's going to cause the air to rise up above the mountains, okay? So we get along the slopes of the mountains, air's rising up from the lower part of the valley. It doesn't always converge like it's showing. It can, and this can be very dangerous in aviation, particularly if you're flying a light or small aircraft. Sometimes we can get these cells setting up where you can see in the central part of the valley, we see this descending air. It doesn't always happen, but it can do that, okay? Now, When the sun sets, the opposite's going to happen. The upper slopes will cool off more rapidly than the lower slopes, so that the upper slope's going to chill the air, cause it to be more dense. It's simply going to start flowing downhill now at night. So both slopes, they're showing flowing downhill, converging at the bottom of the valley and rising up again. Again, it doesn't always do that. But one of the things the lower picture will do is at night, it can take that colder air, which is heavier and denser, and cause it to fill up the very bottom of the valley. That's called cold air ponding, and that can result in freezing temperatures down at the very bottom of the valley and above freezing temperatures higher up. So there you go, valley breeze and mountain breeze. Chinook winds. Chinooks are something that are going to happen typically on the east side of the Rocky Mountains. And this is when we have a westerly flow. So picture a westerly flow of air coming across the United States there, rising, being forced to lift on the west side of the Rocky Mountains. And if it reaches dew point and saturation, it's then only going to start cooling off at the moist adiabatic rate, which is lower than the dry adiabatic rate. So it reaches the top of the mountain, the moist adiabatic rate, starts flowing down the slope on the east side. As soon as it starts flowing downhill, it's no longer at the moist adiabatic rate. It dries out quickly. So that air is flowing down the east side now at the dry adiabatic rate, and it's warming up at that rate, which is a higher rate than the moist adiabatic rate. The whole point here is that what happens is that in Chinook winds that cross the Rockies, the air is going to be warmer by the time it reaches the ground level down on the east side of the Rockies than it was on the west side. It doesn't really affect us at all down here in Arizona. So yeah, anyway. Now the other thing they've got set up here with this chart is the Santa Ana winds. This is something that tends to happen about this time of year, September and October. If we get a big high pressure set up over the Rocky Mountains or the Great Basin area, remember what air does around a high pressure system. All right, what it does, it's clockwise and outward. So what's happening is this high pressure is basically pushing air out toward California. Also, this area is a higher elevation than, say, the coastline of California. So this air can pick up a lot of speed. Then it gets squeezed through a pass in the mountain range in Southern California called the Santa Ana Pass. And that further can cause a funneling and an increase in the wind speed. We can get very high winds funneling through the Santa Anas and hitting Southern California. And this is particularly a problem in the dry fall down there if we get a fire going. These Santa Ana winds can fan fires and blow them up into firestorms. Something that was discovered in Boulder, Colorado a few decades ago, we have a couple of atmospheric research centers in Boulder, Colorado, was very strong winds and sometimes Chinook winds coming down the east side of the Rocky Mountains and hit vertical protuberances and then spinning off little tornado-like features down both sides, causing damage in the town of Boulder and some of the other surrounding communities. You can see here the wind, sometimes we get these wind gusts of 100 miles per hour. They term these mini tornadoes as mountainados, and it's the first place they've been recognized around the world. Another type of wind is a Katabatic wind, okay? Basically a gravity wind, but generally where we see these kind of winds develop is over cold, high plateaus, and then several factors can cause that wind to start flowing down the slopes. As that wind, cold, dense wind starts flowing down the slopes, it's being pulled by gravity, so they can pick up quite a bit of speed, all right? We get them various places in the world. Greenland, the coast of Greenland get a lot because if you can picture Greenland, that's an ice sheet that's 10,000 feet of ice in the center, very cold air and very high. So when we get low pressure, say pulling that air out toward the coast, that can really pick up a lot of speed and just blast these coastal areas. I'm from British Columbia, and we get them along the coast of BC in the winter. We call them outflow winds, and I've seen these winds blow at 60 miles an hour for several days at a time. So those are Katabatic winds, basically driven by gravity, where this cold, dense air flows downhill. And finally, we have these things called dust devils. If you look on the left there, there's a link I've given you to from one of the Spirit rovers on Mars. We didn't know this, but we get these dust devils on the surface of Mars. It's pretty unusual considering how thin the atmosphere is there. Not completely understood or that well understood how they develop, but we certainly see them develop whenever there's in the summer, whenever there's a lot of ground heating. So it might have something to do with differential heating on the ground surface, not completely sure. Then on the right, we have these things called haboobs. What a haboob is when cold air falls out of a thunderstorm. It can pick up dust along the ground, and it can flow out very rapidly in all directions. And we'll talk more about those when we get into thunderstorms and tornadoes. Okay, that's it for this chapter, and we'll see you later.